criminal things happening.
Yeah.
Hi.
Hello. Hi, Arwen. Nice to see you all. Hi, Leo. All right, we're gonna get started soon. So what you see today is we don't have a separate document for writing. The writing will go directly on our investigation. We're going to be looking at a case study. A case study is a case scenario where we're trying to solve a real world problem using our understanding of chemistry concepts. So we're going to be looking at the case study, what the problem is, and then learning a little bit about chemical reaction and going back to collect data and try to solve the problem. Hi, Leo, welcome. We're doing a case study. If you're on Explore Learning, it is the last investigation that you see. So give me a thumb up if you are able to get into the investigation. Give me a thumb up, a signal that you're able to get into where we are looking at. Sean is good. How about you, Aaron?
Yeah.
Yeah, Austin is coming in. Leo, how are you doing? Are you able to get into Explore Learning? Good. Neil, you're good? Okay. And Austin, you're joining us. So let's get started. Hello, Austin. Austin just setting up the video right now. All right. Hey, Austin. Okay, so today we are going to be a forensic scientist working in the Secret Service laboratory. What is a forensic scientist? What's a forensic scientist, Austin?
I don't really know. Oh, the sciences that studies history?
Study of history?
Can I share my screen?
Well, I'll let you share your screen after we...
It basically, it's like that scientist that usually when there's like a crime scene, they gather up the evidence and stuff like that.
Yep.
And they like analyze it and to find like hints to see like what really happened and all that stuff.
Perfect. So forensic scientists are scientists who collect data and analyzing evidence at a crime scene, right? So their goal is to solve crime scenes. All right, so Arwen, as I'm going through, I'm gonna let you present after I showcase a few things, okay? So the Secret Service was established in 1865 to investigate the counterfeit.
It's almost like when my mom was born.
1865 of United States currency, such as dollar coins. Last week, Secret Service agent received a tip amount of criminal group that was making fake gold coins. The agent raided the suspect's warehouse and found coins that looked like $50 coins from the year 1915. So here's a little snapshot of what was that like. Okay.
What are they doing?
Well, they're arresting people who are making fake coins.
It's counterfeit currency. And this looks quite real.
Yeah, it does look quite real.
Minting coins is very hard to show if there's counterfeiting, but the banknotes, they have multiple security features to make sure it's not counterfeited.
Yeah, the machine that they scan, they're very strict about it. Once they detect any counterfeit, they don't even look at it and they take it right away. All right, so I got Sean back. All right, so Yuchun, can you read this first part? What do they find? Can you do a summary?
They found 1,000 $50 coins that look like they are from the year 1915. The real gold coins are worth 25,000 each. So for 1,000, that'd be $25 million of fake currency.
Miss Cathy, I just crashed.
Yeah, I saw that, Sean.
Yeah.
So
I
take
just
a moment
came
to
back.
log back in. It's okay, no worries. Okay, when you're ready, Arwen, can you read the next part?
They also found, well, I'm just going to mine. They also found copper and silver coins that look like the gold coins. Can I read the next one?
Take it.
There were also blank copper coins and a machine that stamps the 1915 image into these coins. I know one of these. These coins like give you the coins and it's really fun. These coins,
Austin, can you take the next one?
the circle coins.
Austin, can you
When
read?
they cut one of the gold coins, they found that the inside was made out of copper. So it's
And
fake.
Sean?
Okay. The suspects may have changed copper coins to look silver, then changed the silver-looking coins to look gold.
So they found a lot, right? Here are the evidence. Aaron, can you read the evidence?
The Secret Service is now preparing to prosecute the suspects in federal court. Evidence from the warehouse is shown below. As a forensic scientist, it is your job to prove how these materials were used to make the coins appear gold. We need you to identify and replicate the methods that the suspects used.
Okay, so to support the evidence of their arrest, these substances were found, zinc metal, zinc chloride solution, and we found counterfeit coins. So our hypothesis, let's take a look at our hypothesis. On the periodic table, we have a series of metal that are considered metal. They have the metal property, and they are arranged in the order of reactivity, or the activity. The reason that they're active is they want to be stable. And we're going to go into the student handbook to learn more about why these things want to react. They're reacting with other materials. So the general gist in this reaction is you have a neutral atom and then you combine with an ion and you create a reaction. So there are two hypotheses that were proposed. These are the two different chemical reactions that fake coins were made. And our job is to figure out which was the process of making the counterfeit. So before we actually go into this, we need some background information. And Arwen, if you like to present, I will invite you to present the handbook. We're going to go into the handbook and then come back to the scenario and to collect data to decide which chemical reaction was carried out. Would you like to do that, Arwen?
Wait.
If not, I can share. Arwen, how are you doing there? Would you like to share or you want me to share? Brayden, you know a famous forensic scientist? That's really cool. Arwen, is that a thumb up I share or you're still trying to figure it out? Give me a thumb up if you want me to share.
Okay.
Okay, so
Look, the thingy.
okay, all right, good. So we're on handbook and we're gonna go a few steps back into the fundamentals of chemistry and starting with the structure of an atom, right? Everything starts with the periodic table. So we're going to go click next. So in an atom, we have all of these parts. Xiong, what are the parts of an atom?
There's an electron, proton, neutron, and a nucleus.
Okay, great. So we can click each one of these parts and just examine how they are put together. We got in the nucleus, we have the positive and the neutrons. Click next. Neutrons have no charge. Then we have electrons, which are orbiting on the outer shells of the atom. So there's a tremendous force, nuclear force, that's preventing the positives and the negatives charges from collapsing. Okay, great. Click on next. And I know that you all know what these parts are. Should we just skip this part? We know the parts of an atom, where you can quickly put them in. Okay. Okay. Submit. Which one has no charge?
Neutron.
Neutron has no charge. Great. All right, next. So what does that mean? Every atom has different number of protons and electrons, but their net charge is 0. So the natural occurrence of atoms are 0 charge, or also known as neutral charge, neutral atoms. Next. So if you have 5 protons, you're going to have 5 electrons to balance that positive and negative charge. Next. So positive 4 plus negative 4 give you a 0. Okay. Now there's sometimes you have more of a positive charge or a negative charge, and so you create ions. Ions are atoms that have charges. Positive ions are called cations. Negative charges are called anions. So those are some like technical terms that comes into play when we're examining the specific chemical reaction. Next. So in this exercise, it just allows you to take away some electrons, remove some electrons, add or remove, and to create charges. So you can, or when you can click on add electrons, remove electrons, and you can see the charges, overall charge decrease. If the net charge is negative, we call that an ion. If the charge is positive, we call that cation. Next. So we got the basic structure going. Now let's take a look at how that comes into play in terms of bonding. So next, click on next. I'm going to skip some of these simple concepts so we can get to the main point of this work. So chemical bonds has to do with the chemical structure of the atoms, right? The creation, the presence of electrons, the movement of electrons really creates that connection. And so let's click on that play button and just create a bond between 2 atoms. And here is an example how bond is formed. Now click on next and we're going to examine how that actually works.
Which bond is this, covalent or ionic?
So R1, can you click on the next button, not that one, the one before that? Click on the yellow box. Let's see if we can click on the left mouse.
Oh.
Okay. I'm going to, let's see if I can take a remote control request. I'm going to skip over some of this work. Okay, so this is for everybody. Neil, I know you're really interested in different type of bonds. So how do bonds really form, right? Something has to come
Can I say-
together. Go ahead, talk.
So this one here is called a covalent bond. So atoms, there's something called the octet rule. It means that the valence electrons of an atom, valence electrons, the outer electrons, must equal to 8, 2, or 18. And it changes depending on which shell it is. Anyway, what the covalent bond is that two atoms can bond if they come together and start sharing electrons to fulfill the octet rule, and then they don't fall apart, because if they did, then they wouldn't be sharing electrons and one of them would lose the octet rule. So they're bonded by sharing electrons.
Thank you, Neil. Absolutely. So the driving force for making a bond, for making friend, is to be stable, right? If you think about why do they want to make these structures to be stable? What makes them stable? 8 electrons on the outer shell. Doesn't matter how many electrons they have it together, but they want to meet that number 8 rule. So they can do that 2 different ways. They can share with someone else, or they can donate. If they have extra, they want to donate that extra. If they don't have enough, they could share. In a covalence bond, it's involved in the sharing of electrons. Remember, in an atom, the only thing that can move around are the electrons. So in the process of making bonds, you'll see the electrons are shifting around. Covalent, sharing. What about the next part of the bond? There's another type of bond, and Neil, you want to talk about this?
Yeah. So what happens is that if, let's say there's an atom, or let's say there's an atom with a negative charge, aka anion, and an atom with a positive charge, aka cation. Well, what usually happens is that, for example, in the case of salt, it's made of chlorine and sodium. Chlorine is missing an electron in its outer shell. The sodium has an extra electron. The sodium wants to get rid of the electron. The chlorine wants an electron. When they come together, the sodium throws the electron over to the chlorine, and they're happy about that. The chlorine becomes negatively charged. The sodium becomes positively charged. So the electromagnetic force pulls them together.
I really like that example you were giving, Neil. Thank you. And so in this process called ionic bonds, and this is through donation. If one ion has an extra electron, it just want to give it away. Doesn't want it anymore because they want to be happy. I like that word you are using, be happy. To be happy, it needs number 8 electrons. So by donating, and if I replay this by donating its extra electron, you see that it's really happy. Okay. So good example, sodium and chlorine. Ionic, covalent. Here comes your example. Sodium, chlorine. Sodium want to donate the extra electron. Chlorine wants to take it. Now they're all happy. They all have the correct number of electrons. So here are some examples. Covalent, share. Ionic, transfer. See, there's only one thing that's being transferred, and these black circles that you see are electrons. Atoms hold their electrons in shells. This is an example of electrons are being transferred. And it actually give you this process of filling in, right? So it gives you some examples of different shells. If you think about atoms, every level has a shell, and electrons can take on different energy levels. First, it's going to fill out the first shell. The first shell takes on 2 electrons. Then it takes on the second shell that can hold up to 8 electrons. That's where that magic number 8 is, and that's the happy state. That gives it a total of 10 electrons. And chlorine has a total of also 10 electrons. And notice the outer shell, both of these have has the number 8 met. The third shell can also hold up electrons. And sodium has 1 extra on its outer shell. Chlorine has 1 less filled. So right now on the outer shell, chlorine has 7. Sodium has 1. Look at that green color, that has 1 shell. So it's not happy with that 1. And chlorine's not happy with 7. They want the magic number 8. So what's the solution for that? Why don't you just give that extra away to chlorine? Chlorine with an extra 1 will meet a number 8. Giving away number 1 by sodium, it will have a number 8. It will have an 8 active root. It'll meet the active root, right? And number 8. So that's how it works. By transferring the extra electron, it meets both electrons become happy. Okay, so to summarize, electrons are moving. They are moving to make the atoms happy. To be happy, it means they are stable. Stable means they're less likely to have a chemical reaction. If they're not, then they're going to be reacting. And this is what the reaction looks like. I'm going to play that again. Electrons are being transferred over to make each other happy. Right? By giving away 1, it has its valence electron has 8, and this one has 8 as well. Right? 1, 2, 3, 4, 5, 6, 7, 8. Questions about that? And in that instant, we're saying sodium is losing electron. Chlorine is gaining, losing, gaining. These are the reactant, and they're not stable because they're not happy with the number of electrons. In their final product, they become ions. They're more stable when they're ions by forming that extra bond. And to form that bond, they transfer that electron. So that's the entire process of creating chemical reaction, going from unstable to stable. Okay, let's see. Should we try this? All right, let's try this. Aaron, can you read the question?
Here we see the valence shell of oxygen and magnesium. How will electrons react to make a stable product?
Okay, valence means outer shell. So we're just looking at the outer shell. So for oxygen, it's the green circle. For magnesium, we're looking at that outer shell, which is also green. So Sean, how many valence electrons does oxygen have? Just count the number.
All right, let's see. 1, 2.
Just the outer one.
The outer one. The outer one, it has a total of 8.
Well, let's count. The one that is dark circled.
Oh, so if it's in a pair, then it's probably 4.
It's 1, 2. I'm gonna annotate for you.
1, 2, 3, 4, 5, 6.
1, 2, 3, 4,
5, 6, 7, 8. I said 8.
5, 6. Now, the one over here is not really an electron. It's empty. Can you see?
Oh, I see why. Because it's not highlighted.
It's not highlighted. Yeah. So this has 6.
Yeah, 6.
Brayden, can you count the number of valence electron for magnesium?
So there are just 2.
Good. I see it. All right. So is oxygen happy with 6?
Nope.
Is magnesium happy with 2? Okay.
Nope.
How do we rearrange this so everyone is happy?
Can I?
Arwen.
You move the magnesium atom to the electronics, move it to the other small one, oxygen atom. Then both of them will be happy.
Like this, going that way?
Yeah.
Okay, so which one will be my choice? A, B, C, or D? Anyone can answer that. A, 1 electron. B.
I pick B.
D.
You think it's D?
Oh yeah, it is D.
Oh, do you agree, Leo? D. Yep. So we got it. Right. We understand this process of transferring of electrons, which is happening right here. I'm going to react again. This is called a chemical reaction, and this is the heart of the chemical reaction we're going to speak about, transferring of electrons to create counterfeit coins. Let's identify how the suspect could have made a fake coins. Cut the fake coin. I'm going to go back because I want to cut it, right? So on the outside, looks like silver. When you cut it, it's really made of copper. So the inside is all copper, and people are paying for the silver price, which are different category. So the coating of one metal onto the surface of another is called a metal plating, right? So when you do a metal plate,
It's like a plate.
It's like you preparing for a plate, but you're coating it through chemical reaction. Metal plating use a type of chemical reaction called redox reaction. And I want you to take home today the word redox reaction. It involves the transfer of electrons that you saw in the previous examples when we're talking about the structure of atoms. Why does this happen? Because we want to create stable conditions. So let's see how it works. I'm going to call on people to read the different sections. And Austin, can you read this portion of this? Austin.
Reactions that involve the transfer of electrons are called redox reactions. In redox reactions, one atom loses electrons and another atom gains electrons.
And very good. And when that happens, they can actually change its chemical property when electrons are being transferred. Now, there are two special terminology that are involved in the redox reaction. So there are two processes. One is oxidation. Aaron, what is oxidation?
When something turns color, changes color because of oxygen.
Okay, sure. You can take a look. You can read this section.
The loss of electrons called oxidation.
Yeah, oxidation is the loss of electrons. Giving away electrons is called oxidation. And there it is. Here's an example of oxidation. In the second part of the reaction is called reduction. That's how redox came about. Reduction, oxidation, redox. So what is reduction? Leo, what is reduction? You can read that to us.
The gain of electrons.
Gaining of electrons. And here goes. Here's what it looks like. Gaining, receiving. Now watch this process again. This atom right here on the right was losing electrons, and that electron being passed through to the other one. Right? So the purple atom is gaining, the green atom is losing electrons. And therefore, we call that redox. This is called transfer electrons. We've seen that several times. Redox reaction involving the transfer of electrons. The way to remember it is red ox. That's just a shortcut. You can also remember whether an oxidation reduction is losing or gaining electrons by remembering this mnemonics called oil rig. Oil means oxidation, stands for oxidation is loss. Rig means reduction is gain, right? So when you are looking at reaction, you have to identify which part is losing and which part is gaining electrons. Some cool way of remembering. Questions about this part? What are we talking about? Bring everybody back. We're talking about a special chemical reaction that creates counterfeit coins. And this reaction requires simply the transfer of electrons. Brayden, can you read this part?
Chemists check the loss or gain of electrons by looking at the oxidation rate of reactants and products.
Good. Reactant is a starting material. Product is a final new material. We can take a look at the oxidation states we can track the oxidation states to see which one is gaining and which one is losing electrons. And this is simply a measurement of charge. Keep track of the charge. Erin, what's another word for reactant? Reactant. In chemical reaction, what's another word for reactant? What does this word mean? Does anybody want it? Does anybody know? Yuchen, what is reactant?
This would react.
Reactant means the starting material, what we
Yes.
started with. Right, good. First, we need to look at the charge, right? So to keep track, which one is losing or gaining electrons, let's take a look at the starting situation.
None of them have any charge and don't have any oxidation state.
So just to compare, oxidation states are really just the charges that was attached to the atom. So in the beginning, every atom was neutral. Yep, but they're not stable. They're not really happy. So they're going to carry out a chemical reaction where they're going to be transferring electrons. When sodium and chlorine meet each other, they're going to be super happy, undergone redox reaction. So product is our final material that's being made through this reaction. By the way, what is a chemical reaction? What is a chemical reaction, Neil? And right now we're talking about a very specific type of chemical reaction, but in general, what is considered a chemical reaction? Xiong, what is a chemical reaction?
Like when two chemicals when two chemicals combine and they have like a reaction.
Good, that's a typical way of addressing what a chemical reaction is, but to define the definition without using the word, it's creating a new material. Anything that can produce new material is an indication of a chemical reaction. There are different kind of interactions, right? The chemical reaction creates a new material. An indication of a chemical reaction could be a color change, temperature change, formation of lights and heat, changes in texture. So we are talking about a very specific type of chemical reaction called redox reaction. And this creates a new material, which is a counterfeit coin. Okay, does that make sense? Bring you back a little bit. So you're going to hear word reactant and product because it came from the idea of chemical reaction, starting material, new material. And during this reaction, through this reaction, there's a transfer of electrons. So think logically, electrons are transferred. Well, let me just ask you this question, Austin. Which way does the electron transfer from? Take a look at the reaction simulation. Which way is the electrons moving? You can
Moving
say,
to the green one.
and now you can see the words of the atom. Can you talk about the names rather than the color? Austin, do you want to answer that part? How is the electron being moved?
I don't know.
Can you see the movements of this electron moving?
Yeah.
Where is it coming from and where is it going?
Is it going from the sodium atom to the chlorine atom?
Good. It's coming from the sodium atom. It's moving towards chlorine atom. And so let me ask you the question, is sodium atom gaining an electron or losing an electron? So gaining,
Losing. It's losing.
it's losing. It's giving it away. Right? You see that? Very good. And is chlorine gaining or losing electrons?
Gaining.
Gaining. Good. So, and see if that makes sense to you. If sodium is losing an electron, It's losing a negative charge. So now it's becoming positively charged. And therefore its oxidation state is +1. Really, when we're talking about charges, it's equivalent to the oxidation state. But the way we express both are different, slightly different to indicate what we're speaking about. So
they're not always. They're not always the same.
Right, there are cases that there are multiple oxidation states, not always the same. So we have this indicator. Can you identify how they're expressed differently? How is charge and oxidation expressed differently?
Oxidation has like the plus before the 1.
Good. Just the way the annotations, how we're writing it. For the most cases, it's the same in this case, right? So chlorine is gaining that electron, it's gaining that extra negative charge, so it's becoming negative. And we can say that oxidation states is becoming 0. So to keep track of how oxidation states are being changed, we started off with 0, ended up with +1. And for chlorine, it started off with 0, ended up with -1. That's how we keep track of the oxidation state. And by looking at that, we're able to identify the oxidation reduction products, right? So here's for single atoms and ions, right? Like sodium and chlorine, the charge and oxidation are the same number. When we're talking about polyatomic atoms, they are going to be slightly different. Okay, so this is the case that we're saying that oxidation and charges are written differently. Oxidation state has the charge written before the number to indicate that difference. Okay, so to answer this question, how does oxidation state relate to redox? Erin, can you read this part?
If an atom's oxidation state increases, that atom has lost an electron being oxidated.
Does that make sense? So if the number becomes more positive, that means the atom is losing electrons. Does that make sense to you? Increase meaning the number becomes more positive, right? So we went from 0 to +1. So by getting rid of negative electrons, it's becoming more positive. So that actually makes sense. Mathematically, that makes sense. Here's an example of that. We have 0 oxidation state, neutral atom, and then I give it away, transfer the electrons away. Now sodium becomes more positive. We're saying the oxidation state is increasing. So oxidation, so we're saying sodium is being oxidized because it loses an electron. Remember oil? If an atom oxidation state decreases on the reverse, the atom has gained electron. This is the second half of that reaction where chlorine is gaining that electron, so the oxidation state decreased, it becomes more negative. Okay, so we're gonna do a practice. Can we start with Leo? We're going to assign oxidation states for each reactant and product below. Okay, so let's try it. For magnesium, what is the oxidation state on the left?
Zero.
Why do you say it's 0?
Because it doesn't. Because in the MG, it doesn't have any 2+ or 2-. It just has no oxidation state yet.
Beautiful. Naturally, atoms are naturally neutral. When there's no charges, that means this charge is 0, it's neutral. Okay, Braden, magnesium 2+. What is the oxidation state of magnesium 2+?
+2.
+2. Excellent. In this case, when we're talking about a single atom displacement, the charges is equivalent to the oxidation state. Going on to Xiong, sulfur.
Sulfur is -2.
So we're looking at this sulfur atom here.
Yeah, I think it's -2.
Why do you say it's -2?
Because like on top it says like it has like sulfur and then -2 on top.
Okay, so are you looking at the one on the left or the one on
The one on the right.
So it's referred to here, not this one. Does that change your answer, Xiong?
Yeah.
What's the answer?
Oh, so that would be 0.
Good. So you recognize we're looking at the natural atom. Go ahead, Arwen, you can do the next one.
It is -2.
Good. We got it, right? So we're able to look at the atom, say if it doesn't have any charge, the oxidation state is 0. It's important to understand the oxidation state because we are trying to keep track of where the electrons are moving. The only thing that is moving within an atom are the electrons. And by understanding how it's moving, we can understand how the reaction was created. Okay, so now requires you to remember some of the terminologies we learned. That there are 2 processes in the redox reaction, oxidation and reduction. Is magnesium oxidized or reduced? What does oxidize mean?
Oxidized.
Neil, can you explain what does oxidize and reduce?
Oxidized means that it loses 2 electrons.
Yes.
Here, magnesium lost 2 electrons, and since electrons have negative charge, it makes sense that it says +2. I meant 2 plus, not +2.
Mm-hmm. And so, Neil, for those of us who are not able to remember which one is losing and which one is gaining, how do you remember the 2 processes? What's the best way to remember?
Oil rig.
Oil rig. Good. All right, here's the inventory of materials in suspect's warehouse. Let's look at the evidence from the warehouse and investigate what type of metal plating was used to make the fake coins. We have zinc chloride and zinc metal.
Welcome to Explore Learning STEM case on electrons and...
That was an accident. Let's close that. All right, I'm gonna take you on. So there are 2 types of redox reaction here. And Xiong, can you read this part?
And plating reaction, one metal A is plated onto another metal B. We'll look at 2 types of plating, additive and displacement. Learn about additive plating.
Keep on reading.
Okay. Metal A, metal B. Plate metal A onto metal B. A layer of metal A atoms are added to the surface of metal B.
Yep, so you're just adding, right? Additive. You're adding an extra layer on top. You're adding an extra silver on top, but the bottom is still copper. What is displacement plating? Brayden? Brayden, what is displacement plating? So what happened to B?
Like it gets a bit like smaller.
Yeah, B becomes smaller and it's being replaced by what? By metal A, right?
Yeah.
So displacement means replacing. So instead of adding things on the top, we actually took a layer off and then added on top of it. Took a layer and replaced it. Excellent. Now it allows us to take a closer look at the atomic level. These are the atoms in metal B, and watch what happened. Additive plating requires a solid metal B, so all of these are neutral, no charges involved. And then here comes solid metal A, it's also neutral, and let's see how they are interacting. Here comes an ion metal A, and this is where you see oxidation. Arwen, can you read what is happening here?
First, an electron is lost from an atom in the solid metal A. This causes the atom to become an ion, right?
Yep.
This is an addition reaction because the atom has lost the electronic.
Good. So in the metal A, there's some interactions, which is the electrons are being transferred. The ions of metal A is smaller than the neutral atom. And so you see an oxidation because the electrons are lost. Oxidation. Austin, can you read the next part?
This is reduction reaction because an electron has been gained.
So one electron, A, metal A, is losing, the other metal A is gaining. So a redox reaction is a paired reaction. That electron has to go somewhere. It's not being destroyed. It's transferred to somewhere. And you see this electron, there's this metal here is taking in that electron. Okay. Aaron, can you read this part?
The neutral atom now forms a bond with the atoms of metal B.
Okay, so once we create the ion, now there's the opportunity for bond formation, right? Why do they want to form bonds? Why do they want to look for friends? Because they're not really happy. They're not stable. They need to create a stable condition. And this is how you're creating the plates, how you do the plating on top. And this process repeats until the surface of metal B is covered by atoms of the metal A. And the process stops. Yuchen, can you read this part?
Okay, I'll read this part. The bond that holds metal A and metal B together is called a metallic bond. In this type of bond, metal atoms share their valence electrons with many neighboring atoms.
Yes. When you get a bunch of metals together, they're really happy because they have so many electrons to move around, and they're creating that happy valence electron number, and they're forming these metallic bonds. All of these situations allow them to share these electrons, right? So look at these movements of electrons. It's called a sea of electrons because they just move randomly anywhere. Pretty cool. This is what makes metal a good conductor of electricity because of these movements of electrons, right? They can transfer electricity across. Now, in a covalence bond, which is different from metallic bond, covalence is sharing, metallic bond is like sharing between all valence electrons. So you see the single pair of atoms versus neighboring atoms. And now you have a more understanding of different type of bonds additionally to metallic. Metallic bond is adding to our vocabulary. Covalent, ionic, metallic. All right, now let's take a look at the displacement plating. Ready for this? What is happening when you're replacing one from the other? Leo, can you read this part?
Displacement plating requires a solid metal be neutral.
Okay, so we have a platform, metal B, there, standing, they're neutral. Pretty happy there. And Leo, can you continue? What happened then?
An ion of metal A
Okay, so some kind of ion comes in. Keep going, Leo.
as an ion of metal A gets close to metal B transfers an electron to the ion.
And this is what it looks like. Remember, the reason that they're transferring the electrons is because they were not happy with their number of valence electrons. So now you see a displacement. You see a transfer of electrons. Leo?
Because metal B loses an electron, it becomes an ion and leaves a solid metal.
Yeah, this is more like exchanging this place right here. Here's an ion, here's an electron for you. Bye-bye, I'm gonna take your space. And watch what happens in motion. There you go. Displacement happens. Metal A gains an electron, become a neutral atom. This atom forms a metallic bonds with the atoms in the metal B, right? So again, they're creating the situation of metallic bonds where the electrons are moving and sharing within the entire network of metals. Brayden, can you read this part?
Atoms of a metal A continue to replace atoms of metal B to create a coating of metal A on the surface.
So that process repeats again and again, right? This process is different from the additive process. It doesn't add on top, it replaces its place, right? Pretty cool. And so our goal is to figure out which process did the criminal case use. So we got to our hypothesis. There are two processes: additive plating, displacement plating. Now we want you to make a hypothesis. Would you like to take a guess? Neil, which one do you pick? Do you think, we don't know much information yet, we're going to take some educated guess. Do you think the criminals used additive or displacement plating?
I think they used additive.
You say yes to one?
Yes.
Okay, what's your reason?
Well, since zinc is more reactive than copper, it will bind to the copper.
Okay, how do you know zinc is more reactive than copper?
I look at the activity series.
Very good.
Zinc is more reactive than copper, which is what.
Right? Zinc is more active. It's easier to oxidize, so easier to lose its electron. So you're saying it will be more easier. Okay. So let's make a prediction, gather some data. One difference between the two methods of plating is how they affect the penny's mass, right? Depending on how you're creating it, the weight is the way for our measurement. Okay, so let's answer this question. Austin, can I have you read the sentence here? What's the question?
Copper and zinc have similar masses. Based on this, how we expect the mass by the coin change in additive plating and displacement plating.
Okay, so we're adding an extra layer on top. Do you think the mass will decrease, stays about the same, or increase? Austin. Take a guess. We're adding an extra layer to the coin. Do you say the mass will decrease, stay about the same, or increase? How many people think it's decrease? Stay about the same, increase. I have one hand for increase. Sean, you wanna help us?
I think it'd stay the same.
Think it stays the same? Why?
I don't think like anything would happen when you do additives. That's why.
Okay, so the mass will stay the same. Neil, do you agree that if we're adding an extra plate, the mass will stay the same?
Yeah. I think
Yeah.
so.
How about you, Yuchen?
I think it'll increase because you're adding something to another thing. If we add something to another thing, yeah.
Yeah, absolutely. And actually, there's a slight increase of, because you're adding more atoms on top, right? So there's an increase in mass. So we can measure some data on mass to help us. What about displacement? Plating. Austin, do you think the mass will decrease? If we're just replacing a layer of copper with zinc, do you think the mass will decrease, stays the same, or increase?
I think decrease.
Why do you say it's decreasing?
Because I don't know.
Well, to answer that question, we kind of have to figure like, what's the mass difference between zinc and copper, or are they close? Do you have the periodic table open? So the answer to this, if you're just replacing copper with zinc, they're roughly the same mass, right? So their atomic masses are similar. So their masses are the same. So now, the easiest way to figure out what the reaction was is by collecting data on their mass. Right? So we took these coins, we can simply place them on a scale and see what happens. Does anybody else want to take over the remote control on this? Arwen, you want to do this? I'm going to give up the remote control. Why don't you place the copper coins and gold coins on the scale and give us some data there? Okay, so we got 26.95 for copper coins, and now take the gold looking coin and place it on top. Okay, we collected some data. Now let's revise our hypothesis. Austin, what do you notice?
The weight has been like increased.
Yeah, there's an increase in mass. Based on our analysis, what does that tell us?
Can I tap this?
You could click on that. What does that tell us? There's an increase in mass. And we talked about the different type of reactions we're seeing in an additive plating versus displacement plating. How did the mass compare? Which one causes a mass increase? Additive or displacement? Sean, do you remember? Which one causes a mass increase? Adding?
The additive makes it more heavier.
So do we go for this, additive plating? Should we go with this? Should we keep our hypothesis?
Yeah.
Yeah, it seems like additive plating is the way to go, right? We saw the initial mass and we say, hey, based on what we know about the reactivity of zinc and copper and based on the initial mass, we want to have the same hypothesis. Now, what you're going to do when you go home, you're already home, but what I like you to do is to continue on with the experiment and just try out different ways of collecting data. Am I sharing? Okay. So click on next, click on experiment. Yeah, I want you to, let's do one together. I want you to review some evidence. The suspect used an additive plating reacting to add a layer of zinc to the copper coin and make them look silver. And you can continue with the experiment. Well, we didn't finish with it. Well, here's some videos on how this can be done. You take some zinc metal, mix it with zinc chloride solution. You can click on that, yeah.
Ooh.
And this is really what you can actually do this in a lab, right?
Yes, but we kids don't know what's the thing. What's the powder?
Mhm. And step 2, we'll watch one more step and then I will let you work on this on your own. You're going to heat it up, stir until the solution boils. So this is just the process. It shows you how to prepare the mixture and shows you the actual plating. Actually, I want to show you step 3. Go to step 3. It actually shows you placing the coin in there. Zinc plating. Click on zinc plating. Arwen.
Your zinc plating.
Prepare mixture. And next, you see that where things are flashing.
Never mind.
Step 3. So this is how it works, right? You take a coin and you put it in there and you wait for a very long time. And then it becomes a silver looking coin. Right? You're coating it on the top. Step 4. And take it out. It looks exactly like the silver coin.
It's bonding. It's bonding the zinc atom.
Yep. So what I want you to take away today is the beauty of chemical reaction. The idea of this redox reaction can create coins that are seemingly different from what they should be. And it's very powerful. Chemical reaction is so powerful in our lives and it changes our experiences. And so remember redox reaction, gaining and losing electrons. If you have time, please continue looking through these experiments. And if you have a different hypothesis from what we talked about, come back tomorrow and we'll share. Okay, everyone, have a great day. Thanks, everybody. Bye-bye.
Bye.